everyone. This is a GATE 2016 problem which is asked in session 1, and this problem is as follows. The value of the integral minus infinity to infinity sin x divided by x square plus 2x plus 2 into dx evaluated using contour integration and the residue theorem is. So based on the question, like we can understand like this is a problem pertaining to complex analysis. Okay, so now let's proceed to the solution. So we will try the question. So the question is like they have asked the integration of minus infinity to infinity sin x divided by x square plus 2x plus 2. Now this total integration I am taking it as I. Okay. So on seeing this expression, like we have to first find out what is the type of this equation. Okay. So based on that, like we can see the type as, like say for example, like it is of the form I is equals to minus infinity to infinity sin x into p of x divided by q of x. So here q of x has no real roots. That is evident from the denominator. For example, the denominator x square plus 2x plus 2 has no real roots. If we are factorizing and if we are finding out, then the denominator has no real roots. Okay, and then the highest power of p of x is less than or equal to highest power of q of x minus 2. So this is also satisfied. For example, the highest power of p of x is actually 0, whereas the highest power of q of x is 2. So 2 minus 2, 0. So this is also satisfied. So if these two conditions are satisfied, then we can rewrite this I as imaginary part of integration minus infinity to infinity. Sin x can be written as e power ix divided by x square plus 2x plus 2. For example, if in the question, if the question they have given cos x instead of sin x, then we have to write real part of e power ix. Okay, since in the question it is sin x, then I am going to write imaginary part of e power ix. Since e power ix is can be written as cos x plus I sin x. Okay. So the question we have now is like we have actually simplified to imaginary part of minus infinity to infinity e power ix divided by x square plus 2x plus 2. So now I'm going to write x in terms of z. Okay, so we can write the same thing as imaginary part of the contour integration over c e power I z divided by z square plus 2z plus 2. Okay, where c is the boundary of the upper half of semicircle. Semicircle mod z equals to r, where r tends to infinity. Okay, so if I want to draw this the plot of c, then it will look something like this. Okay, so c is nothing but the upper half of a semicircle. Okay, and this radius tends to infinity. So now what I do is like, for example, now I have to evaluate imaginary part of the contour integration e power iz divided by z square plus 2z plus 2. Okay, so the contour integration of f of c into dz can be evaluated as 2 pi I into r1 plus r2 plus up to infinity. Okay, and this is by residue theorem. Okay, so where R1, R2 are the residues of the isolated singularities of f of z. Okay, about the contour. So here first I have to find out whether this f of z has any isolated singularities for this contour. Okay, so for in order to find out the isolated singularities, first I have to factorize z square. I mean, first I have to factorize the denominator and find its roots. Okay, so to factorize the denominator, let's take the denominator separately and then let's find out the roots of the denominator. Roots of z. So z is equals to minus b plus or minus root of b square, which is 4, minus 4 into a into c divided by 2 into a. Okay, this I can further simplify to minus 2 plus or minus root of minus 4 divided by 2, which can be written as minus 2 plus or minus 2i divided by 2. Okay, so on further simplification it leads to z is equals to minus 1 plus or minus I. Okay, so these are the roots. So z1 equals to minus 1 plus I and z2 equals to minus 1 minus I. So we have to find out within these two roots which lies in the upper half of the semicircle. Okay, so when I plot this semicircle, minus 1 plus I, like z1 equals to minus 1 plus I, lies in the upper half of the semicircle. So this is a singular point. Okay, whereas z2 equals to minus 1 minus I does not lie in the upper half of the semicircle. Okay, so now we have to find out the residue of z1. Okay, at z1 equals to minus 1 plus or minus plus I. Okay, so we have to find out residue of minus 1 plus I. So in order to find out the residue, like based on the residue formula, like we can actually find out the value of uh, residue at minus 1 plus I. Okay, so the formula is residue of minus 1 plus I is equals to limit z tending to minus 1 plus I into z plus I minus 1, which is nothing but z minus of a. Okay, and the function f of z. Okay, the function f of z is nothing but here e power I z divided by z square plus 2z plus 2. So after finding out the residue for this, I can write I equals to 2 pi I. Okay, this is separate. I is equals to 2 pi I into residue of minus 1 plus I, and that should be imaginary part also. So I equals to imaginary part of 2 pi I into R residue of minus 1 plus I. Okay, so first we will find out the residue of minus 1 at about z is equals to minus 1 plus I. Okay, so if we are going to substitute instead of z as minus 1 plus I, if we are going to apply the limits, then it is of the form 0 by 0. Okay, for example, here if you substitute for z is equals to minus 1 plus I, the numerator also becomes 0 and also the denominator also becomes 0. Okay, so it is of the form 0 by 0. So we have to apply L'Hopital's rule. We apply L'Hopital's rule. So therefore our residue at -1 plus I becomes limit z tending to -1 plus I. And for applying L'Hopital's rule, like we have to uh, take the differentiation of numerator and denominator separately. So since in the numerator I have two terms of z, so I have to apply product rule. Okay, so on applying product rule, e power iz into 1 plus I into e power iz into z plus 1 minus I, okay, divided by 2z plus 2. So this is after applying L'Hopital's rule. And then when I substitute now the limits, then I can easily find out, like it is e power I into -1 plus I, okay, plus 0 divided by 2 times of -1 plus I plus 2. Okay, so again I am rewriting our residue at -1 plus I equals to e power I -1 plus -1 plus I divided by 2 into -1 plus I plus 2. Okay, so now on simplifying this, we will get e power minus I plus I square, okay, divided by -2 plus 2I plus 2. So on further simplification, we will get e power minus I square value I am writing it as -1, okay, substituting for I square as -1 divided by 2I. So this is the residue at -1. This is the value of the residue at z is equal to -1 plus I. Okay. So now coming back to the integration. Integration we have already written as imaginary part of 2 pi I into r of -1 plus I. I mean residue at -1 plus I. So on substituting the value of the residue here, 2 pi I into e power minus I minus 1 divided by 2I. Okay. On simplifying this, we will be getting imaginary part of 2I gets cancelled. So pi into e power minus I, and the e I am taking it down. E power minus 1 I am taking it to the denominator. Okay. So again on further simplification, I can write this as pi by e into e power minus I can write it as cos theta minus I sine theta. Okay, so I am writing this as cos of 1 minus I sine 1. Okay, cos 1 minus I sine 1. Okay, so imaginary part of this is like so when I want to know only the imaginary part, then I can write this as imaginary part of this whole expression will be only the items I have to take. So it will be pi by e into sine 1. Okay. So at last we have find out the final expression of the integration. Okay. So it is pi by e into sine 1. I mean minus pi by e, since there is a negative term here. Okay. So this is the final answer. So can we check this in the option? Yeah. So the option is A. Answer is option A. Thank you.